Hi, I'd like to welcome you to Math 131. I realize we're not on campus today, and I thought I would go ahead and record this ahead of time before our class meets, since it's been so long since I've made a video online. So what you should have already done for me is ran off a copy of the notes that I put on Jupiter Grades, and also made a triangle for me. One of the first things I'd like you to do is to write down some of the squares, because we're going to need these squares. So if on a piece of paper somewhere, you would write the calculations for 11 squared, 12 squared, 13 squared, 17 squared, 24 squared, 25 squared, and 41 squared. So if you go ahead and do that ahead of time for me, before you can go ahead and pause the video. Again, 11 squared, 12 squared, 13 squared, 17 squared, 24, 25, and 41 squared. And that'll get us started on the notes. Okay. So go ahead and pause the video, and then as soon as you get those calculated, you can start. One of the first things I'm going to do is I'm going to share my screen with you, and my screen has these notes. So if you'll get your notes out and a pencil. And I'm going to go to a different set of notes. Okay, all about triangles, geometry review. We have a classification of triangles as follows. I'm going to do the best I can to explain this on your paper. First of all, an acute triangle. An acute triangle is any triangle where all of the angles in your triangle are less than 90 degrees. An obtuse triangle is a triangle in which one of your angles happens to be obtuse. A scalene triangle, and you have a blank right there on your space, but a scalene triangle is a triangle with no sides congruent. And a right triangle is a triangle that has one right angle. I'd like you to note that the longest side, the side opposite the right angle, is called the hypotenuse, and the other two sides are called legs. In an isosceles triangle, an isosceles triangle has two sides that are congruent, and we mark congruencies with this symbol. I'm going to move this symbol down here, meaning that this, which is called a leg, is exactly the same as the other leg. And again, this is true for your isosceles triangle. And again, we mark those with little hash marks like that. I could move that up here. Maybe that's better. The two sides that are congruent are called legs, much like that is in a right triangle. The angle that is opposite the base is called the vertex angle, and the base is one of the non-congruent sides. Isosceles triangle has two sides congruent. Also, what you're going to notice in an isosceles triangle is that the base angles, this angle right here and this angle right here, are also congruent to each other. what we could do is we could actually just go ahead and draw a vertical line straight down here from the vertex angle to the base, perpendicular to the base, and you would see that these two triangles formed are congruent to each other, so their base angles would be the same. An equilateral triangle is a triangle with all three sides congruent. So let me mark this here and trying to take another side. Mark this side and mark that side as congruent. And it kind of comes from the name. If you think of what the lateral muscles are on your side, equilateral, equal sides on your triangle. A triangle, let me take these congruent parts off for a second. A triangle is usually labeled by labeling each one of the angles with a capital letter. For example, I could call this triangle capital A, B, and C. And when we do that, when we name our triangle, each one of the angles with a capital letter, we have a very special way that we then label the sides of the triangle. So if this is side capital A, I'm going to copy that for a moment. The side opposite that angle, which is this one right here, is going to be called side little a. If I give you the angle B, which looks like it's down here at the base of this triangle, and I want to designate the opposite side, what I'm going to do is I will call this opposite side, here's my angle B, I will call this opposite side with a lowercase letter B, and the same thing I would happen with this C across here, this side, this, instead of calling this length from A to B, a line segment from A to B, I would call it little c. Now, one of the first things you were supposed to do after you wrote your squared numbers down before you came into lecture was to make a triangle. And so I'm going to go ahead and stop sharing my notes with you for a second. What I had for each one of you for class today was I had triangles to give each one of you. And what I was going to ask you with your triangle is, and I'll just give you this one for example, is this triangle, which classification would this be? This, in my opinion, is going to be a scalene triangle because none of the sides are exactly the same, but it would also be classified using this angle because this angle is larger than 90 degrees. This triangle would be called an obtuse scalene triangle. Whereas if you had received, let's say, this triangle in class, you probably would classify this as equilateral. All the sides are exactly the same. You could also call it isosceles because at least two sides are the same. And so that would be how I would classify that triangle. And another one you might have actually cut out on your own, since I didn't give you much instructions except say to cut it out. Maybe you actually cut out a right triangle. I would classify this according to its what it looks like. It looks like these two sides are congruent, so I'd call this an isosceles right triangle, whereas perhaps you made a different triangle that was a right triangle. Let me see if I have one here. Got lots of obtuse triangles to give you. But I think you have a pretty good idea on what those triangles are. What I'm going to do now is have you follow the instructions on the Explore activity. If we were in class together, I'd have one of you read the directions. But here is the obtuse triangle that I have. And step number one says to do what? Step number one says take any triangle, and again, any triangle that you drew, and place the numbers 1, 2, and 3 inside each of the angles. So go ahead and place the number 1, 2, and 3 inside each one of the angles. And I'll go ahead and do that. 2, and 3. Step number 2 says carefully tear the 3 angles from your triangle. Carefully tear the 3 angles from your triangle. What does that mean? That means tear off the angle from your triangle. Tear off angle 1, tear off angle 2, let's tear it off, and tear off angle 3. So there are your 3 angles. Would you please read step number 3 and see if you can do that for me? You can pause the video while you're trying to arrange them to show that the measure of angle 1, the measure of angle 2, and the measure of angle 3 must equal 180 degrees. And then as soon as you do that, we'll go ahead and tape it to your piece of paper there. Okay. Okay, so this is what I actually did. And again, I would have you come up to the document camera and try to convince me that angle 1, angle 2, and angle 3 form a line right here. Where are they? Right here. And you try to put them together. And in doing so, then you can see that on this line, we have 180 degrees. And I can't figure that out sideways. There we go. So this leads us to probably something that you already know, and it's the angle sum theorem for triangles. So I'm going to go back to the notes. And share my screen again. So the angle sum theorem for triangles is the 3 angles in a triangle will sum to 180 degrees. If you look at the triangle that I actually placed in the acute triangle at the top of the page, and you add 72 degrees with 43 degrees, and then with the 65 degrees, those should add up to 180 degrees. So our first example we want to look at is if the vertex angle of an isosceles triangle is equal to 118 degrees, can you find the measure of each one of the base angles? Now, in order to do that, what you need to understand is exactly what the isosceles triangle is, again, in the characteristics that it has. So on an isosceles triangle from here right above, isosceles triangle has 2 legs exactly the same, and the vertex angle says that the vertex angle happens to be an obtuse angle of 118 degrees. So what we're going to do is to try to find the measure of the 3 base angles. I'm going to go actually try to do this on a whiteboard. So let me go ahead and share on the whiteboard here. So in looking at a picture, which I would try to draw a triangle with 118 degrees here at the vertex of my angle, understanding that my picture might not look like it's drawn to scale, but if that's the vertex angle and these 2 angles are exactly the same, these base angles down here must be congruent. And since all the angles in your triangle add up to 180 degrees, if I call this measure angle 1, then this is exactly the same angle 1. So I have 2 measures of angle 1 adding to my vertex angle of 118 degrees must equal 180 degrees. It's been a long time since I've written with a mouse on a whiteboard, so I do apologize. So we have 2 measures of angle 1. One of those, since those base angles are exactly the same. To solve this equation, I'm going to subtract 118 from both sides. Two measures of angle 1. If you take 118 and you subtract 180, you'll get 62 degrees. We divide both sides by 2. We get the measure of each base angle to be 31 degrees. So this angle here is 31 degrees, and the other angle is also 31 degrees. Okay, so let's go to the next page in your notes. So while this is a very important theorem from high school geometry, one of the most important theorems, in my opinion, is about a right triangle and only a right triangle, no other triangle. So what I have drawn for you is a triangle, and I do not believe you have this labeled as triangle A, B, and C, but I've got my angle A located at the right. Angle C, because it's drawn with that square, is my right angle, and angle B is over here. Recalling what I do for my sides, opposite the capital A will be my little a, opposite the capital B will be my little b, and opposite the angle C, in this case, the hypotenuse is going to be called side C. The most important theorem that we have, in my opinion, is called the Pythagorean Theorem, named after the Greek mathematician Pythagoras. A triangle is a right triangle. IFF stands for if and only if the square of the length of the hypotenuse, and that's again the side opposite the right angle. If the length of the hypotenuse is equal to the sum of the squares of the two legs. So again, recalling this leg and this leg, one called A, one called B, it says if you sum their squares, if you take A squared and add B squared, it will equal the square of the length of the hypotenuse. It'll equal C squared. So perhaps you've heard before, A squared plus B squared equals C squared. In the illustration I have down below on the page, I have drawn a right triangle, even though it's not marked with a little square right here. But I wanted to illustrate for you this geometric form, which consists of a length of 3 for this leg, represented by those 3 squares, and a length of 4 representing on this side for those 4 squares. And on the hypotenuse, there happen to be 1, 2, 3, 4, 5 squares. And this is called a 3, 4, 5 right triangle. The Pythagorean theorem says if you take one leg and actually square it, so I actually put the square on that leg. If you take the other leg and put a square on it, so I took 4 and I made a square on that length of 4 squared, it will equal the length of the hypotenuse squared. A squared plus B squared is supposed to equal C squared according to the Pythagorean theorem. I think I've got C squared down there. I'm not sure how to make this right now go. Let me see. How can I make that be an exponent? It's not showing up. There it is. Is that it? Okay, so go ahead and put C squared there. 3 squared plus 4 squared, so this squared plus this squared equals 9 plus 16, and 9 plus 16 equals 25, and that's how many squares you actually, if you want to count here, 1, 2, 3, 4, 5, 5 times 5 is 25. That's how many squares you actually have on the hypotenuse. We have something called Pythagorean triples. One Pythagorean triple, and one of the most famous ones, is called the 3, 4, 5. Anytime you have a triangle with sides 3, 4, 5, they satisfy the Pythagorean theorem, and they guarantee that you have a right triangle because of this if and only if statement. If a squared plus b squared equals c squared, then you have a right triangle. And if you have a right triangle, a squared plus b squared will equal c squared. If you have your hypotenuse labeled C. What I now want you to do is try to figure out some other Pythagorean triples. For example, the Pythagorean triple 6, 8 equaling what? 6, 8 what will give you another Pythagorean triple. So if you'll take time to fill in these blanks, 6, 8 blank, 5, 12 blank, 7, 24 blank, 8, 15 blank, and 9, 40 blank, if you'll fill in the numbers, and the way this is set up is the hypotenuse is always the last number in your, there's the largest number. It's always the largest number. It is the hypotenuse. So 6 and 8 are 2 lengths of the leg. Okay, so if you'll go ahead and figure out the a squared plus the b squared, just like I did here, and then we'll go ahead and continue on. So go ahead and pause the video and go ahead and try to do those. Okay, so what you should have gotten for your Pythagorean triples we know that 3, 4, 5 is a Pythagorean triple because 9 plus 16 gives you 25. For 6, 8, 36 plus 64, you should have gotten 10 because 36 plus 64 equals 100. And so the hypotenuse must have been 10. Now, this is not a unique Pythagorean triple because if you look at the 3, 4, 5, every one of these legs got multiplied by 2. And so that means the hypotenuse got multiplied by 2. So 3, 4, 5 is its own unique Pythagorean triple, and 6, 8, 10 is just a multiple of that. If I decided to multiply this by 3, everything up here by 3, I would have a 9, 12, 15 triple, and it would be a Pythagorean triple because 9 squared with 12 squared, which I believe you already calculated as 144, equals 15 squared, which is 225. So anytime you have a 3, 4, 5 right triangle, you multiply by 3 or by 2 or by 4, it will actually go ahead and be another Pythagorean triple, but it's not really a 6, 8, 10 is not a new Pythagorean triple. It's just it's just a multiplication of 3, 4, 5. So let's go ahead and look at the next one that you have in your notes. You have a 5, 12. So if you took 5 and squared it, you'd get 25. If you took 12 and squared it, you get 144. And this adds up to 169. And you might not be quite familiar with some of these squares. However, if you did go ahead and square those numbers that I gave you at the beginning, you'll find out that 13 times 13 is 169. So we have a 5, 12, 13 Pythagorean triple. 5, 12, 13 will make a right triangle. Next, going over to the right, we've got an 8 and a 15. The hypotenuse, if you took 8 and squared it, you get 64. 15 squared is 225. We add those together, we get 289. And 289 happens to be 17 squared. So we have a Pythagorean triple of 8, 15, and 17. Next, in your notes, you have a 7-24 dash. What does the hypotenuse have to be? Now, if you think about this, 7 is not a very long side of a right triangle. 24 is actually rather long in comparison to the 7. And we're trying to find the length of the hypotenuse here. And we're kind of use 7 squared, which is 49. 24 squared, which I believe you got 24 times 24. $96. 8, 4. My eraser at 24 times 24, which is 576. Adding these two together, we get 625, and that happens to be 25 times 25. So the length of this hypotenuse is rather long. It's almost the length of this side. So we have a 7, 24, 25 Pythagorean triple. The last one is a 9, 40. And you should have gotten 41. 9 squared is 81. 40 squared is 1600. When you add those together, you get 1681, and that should be exactly what 41 times 41 is. Forty-one times 1 is 41. 41 times 4 is 164, and you add these together to get your 1681. So again, these are called Pythagorean triples. If you ask me what my favorite is, I really like the 3, 4, 5. And I also like 5, 12, 13 quite a bit. These larger numbers I'm not too fond of, but they do exist, and I don't have to do them over and over again. If I have a problem, I know what they are, And there's many more Pythagorean triples. These are just the ones that are listed on your notes. Okay, let's go to the next page of your notes. Example 2 says classify a triangle that has sides of length 8, 12, and 6 inches. I want you to be very careful how I labeled these sides. 8, 12, and 6. 12 is the longest side, and so I have to make sure I understand that this has got to not necessarily in order of a Pythagorean triple. In fact, I don't think it is a Pythagorean triple, because the Pythagorean triple that I know from the previous page is a 6, 8, 10 right triangle. 6, 8, 10 is my Pythagorean triple, multiple of 3, 4, 5. And in looking at my Pythagorean triple, I go, okay, 6, 8, 10 is a right triangle, but the given information says that I've got 6, 8, and 12. So what is that given information informing me about? Well, if I do try to take 6 squared plus 8 squared, I know that's going to be 10 squared, that's going to be 100, and that is smaller than 12 squared, which was given to me to be perhaps the longest side, which is not the hypotenuse. And since this is larger than that, our conclusion is that this angle must open wider than 10, because 10 makes it the right triangle. And if I open wider than that, what that's going to do is make my angle not be 90 degrees. So that my conclusion is the triangle is scalene, because none of the sides are exactly the same, and as an obtuse angle. I want to talk to you now about a very, very special right triangle. It's called a 45-45 degree right triangle. If two legs of a right triangle measure 6 centimeters each, find the length of the triangle's hypotenuse and leave your answer in exact radical form. So question is where to start. Where to start is always a good idea to write your angles in a triangle. So I would consider that if you wanted to illustrate the right triangle, you might want to try to draw to scale, draw the right triangle. Here, I'll put my right angle in there. Okay. Try to move it over. And label the two legs of the right triangle. Recalling the two legs are the ones that are not the hypotenuse. So this will be a leg of length 6 centimeters, and this has a length of 6 centimeters. And we usually call our hypotenuse, the length of the hypotenuse, little c. So where do you start? First, draw the picture. Then do what? Consider the Pythagorean theorem. 6 squared plus 6 squared equals c squared. 36 plus 36 equals c squared. 36 plus 36 adds up to 72. When you take the square root of both sides, I am always putting a plus or minus sign, because that's the mathematician in me. But I do understand, because this is a triangle and I'm in geometry now, that I can't have a length of a negative length. So I do put the plus or minus, but then I ignore it and I only consider the positive. Simplifying 72 into 36 times 2, the square root of 36 is 6. My final answer for C happens to be 6 radical 2. If you'd like to stop the video if I'm going too fast, you can go ahead and rewind this if you want. So my answer is, well, what's it asking me to find? Find the length of the triangle's hypotenuse. So my answer is the length of the hypotenuse is 6^2 centimeters long. Remember, my original problem was in centimeters, and so I've got 6^2 centimeters. For example 4 in your notes, I have left this blank because I was going to have you guys give me some odd number in class. And since we're not in class, I just decided to come up with the odd number, happens to be 7. It says the hypotenuse of an isosceles right triangle measures 7 meters. So how long is each leg of the triangle? And again, leave your answer in exact radical form. Well, where do you start? I would consider you draw the right triangle. Okay, and the right triangle, let me see if I drew the triangle. Oh, I didn't draw the triangle. So let me go ahead and copy this right triangle for a moment. I'm going to print it down here. And we know the length of the hypotenuse happens to be 7. Since this is an isosceles right triangle, that means both of these sides have to be exactly the same. Let me copy my right angle for you. But I don't know their length. And I could call one of them A and the other one I could call A also. But I believe what I did in my notes is I just said, you know what, I do not know what they are. I know they're exactly the same. So I'm going to call each one of them X. I'll call this one X. And I will call the other one X. Try to copy that. And then, because this is a right triangle, I'm going to use the Pythagorean theorem, which says 1 leg squared plus 1 leg squared equals hypotenuse squared. So I'm going to start with drawing my right triangle. Then I'm going to go ahead and say, okay, 1x squared plus 1x squared gives me my hypotenuse squared. 1x squared plus 1x squared adds up to my like terms of 2x squared, and 7 squared is 49. I'm then going to go ahead and divide both sides by 2. Yes, I divided both sides by 2. And I shouldn't put the plus or minus here. Okay, I need to put a square root on this side. Okay, I left the square root off of that. Square rooting both sides. Getting X to be the square root of 49, which is 7. The square root of 2 is in the denominator. We now have to rationalize this just like good math students. And we rationalize that by multiplying the numerator and denominator by a very special form of 1. So we have 7 radical 2 over radical 2 times radical 2. And giving us 7 radical 2 over 2. So our answer, okay, what are we asked to do? We're asked how long is the leg of each leg of the triangle. So my answer is each leg of the isosceles triangle is 7 radical 2, and this happens to be meters in the problem, so I'm going to say meters long. If it wasn't marked with respect to units, I would just say that's how long it is, just with no units at all. Special right triangle, 45, 45 right triangle. So your legs are exactly the same. You can find the hypotenuse. If you have the hypotenuse, you can find the length of each leg by using the Pythagorean theorem. But another very special right triangle is an equilateral triangle. And so what I want to do is have you understand the definition of an equilateral triangle is that all sides are exactly the same. And I believe your notes have here that this is an X. What I'm going to do to try to make this a little bit easier to consider is instead of calling that X, I'm actually going to call it a 2X. And then I'm going to go on the whiteboard and try to create this very special triangle and all its properties. What do you happen to know about all the angles of this triangle? Well, if this side is 2X, and this side is exactly the same as the equilateral triangle, I know this is an isosceles triangle because two of the sides are the same. Isosceles triangle, at least two sides are the same. And that means these base angles are exactly the same. But if I consider my third, whoops. Uh-oh, what did I just do? If I consider my third side, I didn't mean to go down to the song yet, okay. If I go down to my third side's exactly the same as my other side, since it's called an equilateral triangle. And if I looked at this sideways, these two sides are congruent. So my other angles are exactly the same, meaning my base angles here are congruent. So I actually ended up having three angles being congruent to each other. And since all the angles in a triangle add up to 180 degrees, if I take 180 and divide it by 3, each one of these angles happens to be a 60-degree angle. Maybe you already knew that about an equilateral triangle. Not only are all three sides congruent, all the angles are congruent. So we're going to call this a very special triangle. And I'm now going to go to a whiteboard and show you how we create the lengths. So let me clear everything off of here. Oh, I'm not happy with that triangle. This length, and this length are all the same. If we go draw a perpendicular to the base, remember this base has a length of 2x, this is a length of 2x, and I'm doing this for convenience sake. If this side is 2x, if I draw this perpendicular to the base from the vertex angle, recalling that each one of these angles to begin with were 60 degrees. These two right triangles are congruent to each other, meaning that all their corresponding parts are congruent. So this 60-degree angle at the vertex creates a very special right triangle, and the special right triangle I want to concentrate on. So I want to concentrate on this right triangle, where this hypotenuse is 2x. This is x, And this side right now has an unknown length with respect to x, but this is a 30, 60, 90-degree right triangle, which is going to lead me into a song real soon. When you have a right triangle that's 30, 60, 90 in degrees, to find the length of the... Okay, we've got some sides here. This is called the short leg. This is called the long leg, and I think you can see it's longer because this angle opened wider than 30 degrees. This is called the short leg, and this is called the long leg, and this is still called the hypotenuse. Since we do not know the relationship between these, but we do know the Pythagorean theorem holds true here, what I'm going to do is I'm going to call this length right here. I think I'll just call this B. This unknown length, I'll call this B. Using the Pythagorean theorem, which says that B squared plus x squared equals the hypotenuse squared This gives us b squared plus x squared, which are not like terms, so I can't really add those together, but I'm still using my Pythagorean theorem. My hypotenuse squared is 4x squared. I'm going to subtract an x squared from both sides. If I have 4x squared and I subtract an x squared, that leaves me 3x squared. I'm going to take the square root of both sides. And yes, I'm going to put a plus or minus because that's what I do. The square root of b squared comes out to be b. I'll ignore the plus or minus now. The square root of 3x squared, the square root of x squared just comes out to be x, and we have a radical 3. And this is going to lead me into my song. This length, this longer leg, has a very special relationship to the short leg. So let me go ahead and erase my B for a moment. Erase my question mark. So if you turn the last page of your notes, because you know I want to burst into song. This tune is to the tune of, I think it's called Yankee Doodle Dandy. When you have a right triangle that's 30, 60, 90 in degrees, to find the length of the shortest side, this is the shortest side, it's 1/2 your hypotenuse. See, this is hypotenuse. It's 1/2 your hypotenuse. And when you need to find the long leg, just multiply the short leg by root 3. Oh, don't you use a calculator in special right triangles that are 30, 60, 90 in degrees, or if they're clearly marked that they're isosceles. So please do not try to use a calculator when you have a 45-45 special right triangle, or when you have a triangle that's 30, 60, 90 degrees. So let's do this again. We're going to do an example in class. I only have one example right now, but I've got lots more for your homework. So when you have a right triangle that's 30, 60, 90 in degrees, to find the length of the shortest side, it's 1/2 your hypotenuse. And when you need to find the long leg, remember which one this long leg is, just multiply the short leg by root 3. Oh, don't you use a calculator in special right triangles that are 30, 60, 90 in degrees, or if they're clearly marked that they're isosceles. Okay, so let's go look at the one example I have in your notes. Okay, so the height of the hypotenuse is, I don't think I have this spelled out in the notes. Okay. The length of the hypotenuse is 2 times the length of the short leg. Remember, the short leg is 1/2 the hypotenuse. And when you need to find the long leg, just multiply the short leg and fill this in with square root of 3. So now I want you to try this. I'm gonna pause the video and I want you to go ahead and see if you can, in this particular case, look at the triangle that is given to you. This length is 6. This is a 60-degree angle, which means this is a 30-degree angle. We have a missing side y and a missing side x. It says find the value of x and y below. So we're going to stop the video and I'm going to see if you can do that problem, and maybe you'll be singing my song. When you need to find the long leg, just multiply the short leg by root 3. Let's see if you can do this on your own. So I'm going to stop sharing. I'm going to pause the recording. Okay, so let's go ahead and see how well you did on that. I'm going to go to my whiteboard. Clear this. Actually, maybe I don't want to clear this completely. Let me just go erase some of this. I think I want to keep that relationship up there. So in the problem that you have on your board, or on your notes, I'm sorry. Nice right triangle I just drew. Okay, this is 60 degrees. This must be 30 degrees. And this is 6. This is designated by a Y, and this is designated as the X. 6 is opposite the 30-degree angle, so this is called the short leg. Despite what the triangle I drew on almost all my pictures, it looks like isosceles. So just to kind of ignore that and just go with the notation here. You see the 60 degrees. This is 60, this is 30. This is called the short leg. Well, try to remember the short leg is 1/2 the hypotenuse. So the hypotenuse must be 12 because 1/2 of 12 is 6. And when you need to find this long leg, you could use the Pythagorean theorem all over again if you want. You could take 6 squared plus y squared equals 12 squared, and 6 squared is 36 plus y squared is 144. Subtracting 36 from both sides and getting 108. Taking the square root of both sides and ignoring the plus or minus sign, we then have to factor 108 and simplify this radical completely. I believe 108 can be divided by 36. 36 times, let me see, 36 times, yeah, 36 times 3. So since this is the square root of 36 times 3, the final answer for y comes out to be 6 rad 3. But you don't have to do all this work all over again if you just remember this song. When you need to find the long leg, just multiply this short leg, which is 6, by rad 3. Oh, don't you use a calculator. You don't need to use a calculator in a triangle like this. If you understand the relationship between the short leg and the long leg and the hypotenuse. Okay, so that is this particular problem. This is where in class we would take a 10-minute break and then we would move on into the next page. I'm just going to go ahead and move on to the next page. You can go ahead and pause if you would like to. I'm going to go ahead and go on to the notes though and continue on since I can. Okay, now I want to talk to you about what's called similar triangles. Two triangles are similar, IFF. IFF stands for, again, if and only if. If and only if. The three angles of one triangle are congruent respectively to three angles in a second triangle. These are called similar triangles. Three angles of one triangle are congruent to three angles of a second triangle. Now, in this case, all pairs of corresponding sides are going to be in proportion, P-R-O-P-O-R, in proportion. And I'll do several examples, got a lot of examples here for you to do on similar triangles. Example 5, a flagpole casts a shadow of 20 feet. At the same time, a yardstick held perpendicular to the ground casts a shadow of 4 feet. Find the height of the flagpole. This is how we find the height of things that we can't directly measure. We actually go look in a situation like this where we can actually go ahead and create what are called two similar triangles. Let's look at the triangles that I have drawn for you. Here's the flagpole, and I've got X marked as the length because I don't know the height of that flagpole. And this is my yardstick here that is being held up. At the same time, the sun shines from the flagpole, casting a shadow onto the ground. And you can see kind of the shadow of the flag that I have drawn here. The flagpole has a shadow here of a length of 20 feet. But the yardstick held perpendicular to the ground, meaning that I have a 90-degree angle there and a 90-degree angle there, casts a shadow of only 4 feet. Find the height of the flagpole. What you have is you have two triangles that are similar. They're similar because all three of their angles are congruent. Again, look carefully. I've got a 90-degree angle here, a 90-degree angle in my smaller triangle. And when the sun casts the shadow, this angle formed is the same as that angle. And if you look very carefully, this small angle to the right is both in the little triangle and also in the larger triangle. So actually, if I have these two angles congruent and these two angles are congruent, then of course my third angle there from the sun shining down is also congruent. I'm going to actually do this problem on the whiteboard instead of on my notes. It's just easier for me to do. What I'm going to do is separate the triangles so you can actually see them more carefully. This is my flagpole. I do not know the height, but I know the shadow that it casts is 20 feet. The yardstick casts a shadow of only 4 feet. This length of the yardstick, try to remember, yardstick is 3 feet long. And because these two angles are congruent since they were in the same triangle, because remember, my yardstick was right here. These two angles are congruent, and so my third angle must be congruent up here. And so I have triangles. They're not congruent to each other because one's much larger than the other, but they're called similar to each other. And that means their sides are in proportion. So when I say their sides are in proportion, what I mean is the height of the flagpole is in proportion with the height of the yardstick, and the length of the shadow, which is 20 feet, is in proportion. A proportion is 2 equal fractions to the shadow that the yardstick casts on the ground. There's 2 ways I can look at this proportion. I can look at it and do a cross multiplication. I could actually reduce this first. If I cross multiply, I get 4x equals 60. And then dividing by 4, I get 15. Dividing by 4, I get x to be 15. So it's one way. It's called cross multiply. You multiply the extremes with, they're called the extremes and the means. Or you could go ahead and reduce 20 over 4 because I made them such nice numbers. And when you multiply both sides by 3, perhaps here, this might be the way that you would actually solve this, and you get x is 15. So writing a complete answer, we would say that the height of the flagpole is 15 feet. And that's how we would do that problem. Now, I would like you to try the next problem. The next problem is in your notes. It says, in the figure below, what is the height of the tree? And all measurements are in feet. So if you would go ahead and try to set up the similar situation, understanding that you do have, at this point in time, a right angle, a small acute angle here on both of these, because we're just going to make this a tree. And you could separate, I would encourage you to separate your 2 triangles so that you can actually clearly see the sides that are proportion, and set up your proportions and see how well you do. Okay. So go ahead. I'm going to stop sharing this while you go ahead and work on that problem. Again, stop the video so you can work on the problem, and then we'll go ahead and look at it on the board. I'm going to go ahead and continue. If you are not done, go ahead and stop the video. But I'm going to go ahead and share my reasoning with you. Again, we see this beautiful tree. We do not know how tall it is. I will call it length X because I always let X be my length. The long leg on this right triangle you should have had is 21 feet. The smaller triangle, also with a right angle, they share this acute angle down at the right-hand corner. It doesn't have a label on it, but they share that angle. And so this third angle up here must also be congruent. So we have three angles congruent. We know our triangles are called similar, and that means I can set up a proportion. This given height was 6 feet, and this was 9 feet. All the measurements were in feet. So setting up the proportion, the height of the tree corresponds with the height here of 6. The shadow, or the length of this triangle, is 21, and that corresponds to, in our little triangle, of 9. I could reduce 21 over 9, or I can just go ahead and cross multiply. I think I'll just cross multiply. 9x equals 21 times 6. Dividing both sides by 9. Now, if I reduce this, I wouldn't have such large numbers. But I'm going to go ahead and think that I can do a long division here. This is where I'd ask Jack or Oscar, hey, what do you want to factor? What are your favorite factors for 21? Okay, 9 times 1 is 9. And subtracting, give me 36. 9 times 4 is 36. So our final answer would be that the height of the tree is 14 feet tall. So please make sure that you always answer the question and don't make me just kind of like think about it. Okay. Don't let me just look at all your reasoning and go, I think I know what your answer is. The rest of the notes are for you to try. This is where I would have you go up to the board in your groups, and I would have you look at the unknown lengths on 2 and 3 and the challenge question. And then the why did the tennis player decide to get glasses? Those 18 problems are problems that are going to be assigned for homework. So we're not going to do those today in class. But they involve all these special right triangles, 30, 60, 90, or maybe just using the Pythagorean theorem, something like that. Okay, so go ahead and stop the video, and I want you to try problems number 2 and 3 and the challenge question for your notes. And then I will come back and I will reveal my answers and my reasoning for you. Since you won't be doing this with a partner, you'll just go ahead and do this on your own, and I will be your partner. Okay, so I'm going to stop sharing right now, and I'm going to pause the recording. Okay, I'm going to go ahead and show you what my reasoning was on my answer. So I'm going to go to the whiteboard. I'm not going to go to my paper. So you've got the paper there, so you know exactly what the problem was. You might be asking, what were the colored pencils needed for? The colored pencils were supposed to be to color in those squares on that 3, 4, 5 right triangle, but we're not in class today, so clear all this. Okay. One of the first things I think that you saw was this is a 30, 60, 90 right triangle. It wasn't clearly marked 30, 60, but it was marked 60, and the right angle was here. So of course this has to be a 30-degree angle. When you have a right triangle that's 30, 60, 90 in degrees. In this case, the hypotenuse was given to be 6 radical 3. The hypotenuse was 6 radical 3. So let's go ahead and sing that song and let's get it in your mathematical soul, okay? When you have a right triangle that's 30, 60, 90 degrees, to find the length of the shortest side, it's 1/2 the hypotenuse. Do you know which one is the shortest side? You might not quite know it from my picture right here. Your picture on your paper looks a little bit better, but this is the short leg because it's opposite the 30-degree angle. When you need to find when you have a right triangle that's 30, 60, 90 degrees, to find the length of the shortest side, it's 1/2 your hypotenuse. 1/2 of your hypotenuse is 1/2 of 6 rad 3. So the side has a length of 3 rad 3. 1/2 of 6 is 3. That is the length that's marked X on your paper. So we've got X is 3 rad 3. From here, you can go ahead and use the Pythagorean theorem, and this is designated as Y. And you could go ahead and use the Pythagorean theorem, 3 radical 3, your A squared plus your Y squared equals 6 radical 3 squared, but this is not how I would probably do it. I would probably go ahead and sing the rest of my song. But if you're just a real lover of the Pythagorean theorem, from here, you could just go ahead and use the Pythagorean theorem. 3 radical 3 squared means you have to take 3 radical 3, though, and multiply it by 3 radical 3, which gives you 3 times 3, which is 9, and radical 3 times radical 3, which is radical 9. You would also need to take 6 radical 3 times 6 radical 3, which is 6 times 6, which is 36, and square root of 3 times square root of 3 is square root of 9, which is just 3. And then you get 27 plus y squared equals 36 times 3, which I believe is 108. Subtracting 27 for both sides. 108 minus 27 is 81. And the square root of both sides, plus or minus, is getting ignored right now. Square root of 81 is 9. Well, if I wouldn't do it that way, how would I do it? I would do it by using the song. And so let's go ahead and see what that would be like. Okay, so when you have a right triangle that's 30, 60, 90 degrees, to find the length of the shortest side, it's 1/2 the hypotenuse. And when you need to find the long leg, and this is a long leg, just multiply your short leg by rad 3. If you take your short leg, which is 3 radical 3, and you multiply it by radical 3, you get 3 times the square root of 3 times the square root of 3, which is square root of 9, 3 times 3, which is 9. And that's the easiest way. I think that's so much easier than doing the Pythagorean theorem all over again. So when you need to find a long leg, just multiply your short leg by rad 3. Okay, so let's assume that you have done problem number 2. And if you haven't, go ahead and do it. Stop the video and I will just go ahead and clear all this and look at that problem. to me, this is clearly marked that it's isosceles because of those two slash marks I put there. This happens to be a 2 radical 10. And if that's 2 radical 10, this must also be 2 radical 10. And the length of the unknown, well, actually the hypotenuse, the length of the hypotenuse is called y. Let me get a nice looking y there. Okay, Pythagorean theorem. One leg squared plus the other leg squared must equal the hypotenuse squared. So if 2 radical 10 times 2 radical 10. Two times 2 is 4. Square root of 10 times square root of 10 is the square root of 100, which is just 10. Oh, and this is the same thing. So we have 40 plus 40, which is 80. When we take the square root of both sides, I usually do like to put a plus or minus because that's good algebra. But we're not in algebra anymore, in geometry. We can ignore the negative since we can't have a negative hypotenuse length. We need to simplify the square root of 80. It might be really nice if you would realize that 16 times 5 is 80. That's the easiest way to simplify the square root. The square root of 16 is 4. Your final answer should have been 4 radical 5. And are there any units on this problem? There are no units on this problem. It's not marked in meters or feet or centimeters. So we're just going to say that, you know what? That wasn't even a Y. And looking at the page more carefully, that was actually an R, and this was a W. Okay, the challenge question number 1. I'm going to tell you what I got for the length from A to B. My answer was, I believe it's 21 over 4. And I'm going to show you how I reasoned that one. Again, if you haven't done it, go ahead and try it because you would be doing this on the board with a part. If you've ever done any surveying work, sometimes we do want to know lengths along a riverfront, and it's very difficult to cross the river with a long pole or a yardstick. A, B, C, K, L are shown. B to C is 7. So this is B, and this is C, and this is the triangle ABC. We know that the length from B to C is 7 miles. And that's about all we know from this triangle. I do not know the length from A to B. I do not know the length from A to C. I do not know those at all. In fact, I'm not even going to call them. I don't know them. I'll call this length AB, and I'll call this length AC. The other triangle we have is actually a similar triangle to that. We'll look at it really carefully. it has a 90-degree angle here, so I've got those angles the same. And you go, how do I know they're similar? Well, these are what are called vertical angles, and vertical angles are always congruent here, as we discussed in yesterday's notes. So vertical angles are congruent, which means our third angles are congruent right here. 1, 2, 3 sweeps. So I've got two triangles that are similar, and I can just set up a proportion if I knew which side went with which side. So what else do I know about this triangle? This triangle is called C, K, and L. And what I'm going to actually do, I think, with C, K, and L, I'm going to draw C, K, and L this way. So there's my angle. There's my right angle, and I'm going to move L up here, kind of a reflection over the river. So that's CKL, which was CKL down here. So instead of looking at this triangle, I'm going to look at that triangle. It'll just be easier for me to spotlight the sides I think that are similar. I guess I should keep that as C. And here's my third angle. 1, 2, 3. Okay, so what measurements I know I can measure from C to L. That measurement was given to be 5 miles. This was 7 miles. And C to K is 4 miles. What I'm asked to find is the length from A to B. Because this is a right triangle and I've got a hypotenuse of 5 and a leg of 4, I know, because I know my Pythagorean triples really well, that this must be a 3, 4, 5 right triangle. So I'm going to now set up my proportion, and my proportion is going to be that the height from A to B corresponds with my height from L to K, which is 3. And my length of B to C, which is 7, corresponds for my length of C to K, which is 4. I'm going to go ahead and cross multiply this. This doesn't reduce. So I'm going to get 4 times AB equals 7 times 2, which is 21. And dividing both sides by 4, I got my length from A to B to be 21 over 4. So even though we're not actually meeting in class today, I hope that video will help you with these notes. And they still say the campus is going to be closed until perhaps even Saturday. So here's to good news. I hope that we'll be together on Monday. And if not, we'll be here together in a Zoom, I'm assuming. So if you have any questions, please contact me. And I hope this video was helpful. Have a great weekend. Bye now.